Hello, dear students. Well, once again, I am going to teach you one topic through many videos. Okay, and the topic happens to be our last chapter for this academic year. And the name of the chapter is Electrochemistry. What I've done is I have made two parts of this chapter because this chapter is quite long. If you go through this chapter in your textbook, you'll come to know it's got many pages. So this chapter is quite lengthy. So just to make it quite simple for you to understand, I've put that in two parts. This part will have multiple videos. You must have noticed that the videos are quite short, of 5 minutes duration. Okay, so please go through these videos. I want you to go through these videos for theory. During the class, whether it's online or physical, we'll be spending our time doing some numericals. Okay, so for theory uh, concepts, my dear students, I want you to refer to these videos. Okay, let's begin with this chapter. As the word itself says, electrochemistry, you can see there are two words in this one single word, that is electro and chemistry. So when we talk about electro, I can say it's related to electricity, no? And chemistry, of course, chemical changes. So very simple word, which means it's a branch of physical chemistry that deals with the study of interrelationship between chemical changes and electricity. So when I say interrelation, means chemical changes getting converted to electricity and electricity or electrical energy getting converted to chemical energy. So these two words that you'll have to keep in mind during the entire duration of this chapter: conversion of chemical energy into electrical energy and conversion of electrical energy into chemical energy. This is what we'll be looking at in this chapter. Now, which is that principle allows something like this to happen? It is the redox reactions. Now, what are redox reactions? Redox reactions are a combination of oxidation reduction reaction taking place simultaneously. Remember, we did this chapter in detail in 11th standard. Now, what is oxidation? It is loss of electrons, and reduction, gain of electrons. You must have noticed, my dear students, for electric current to be generated, there should be flow of electrons. No? So that is the principle behind ensuring chemical energy getting converted to electrical energy and electrical energy getting converted to chemical energy. Let's take a look at how that conductance takes place. No? In any conductor, there is this phenomenon of conductance. No? So in a copper wire, it's a solid substance. You can easily make out whether it's a conductor, it's a non-conductor, whether it's conducting or not conducting when it comes to solids. But since we are studying chemistry, my dear students, we will be speaking mostly about solutions. Do solutions conduct electricity? Yes, they do. Okay, and such kind of solutions are called as electrolytic solutions. Okay, so let's compare both the electronic conductors, as in the solid substances, and also the electrolytic conductors, which are solutions. So conduction of electricity occurs by the migration of electrons through the conductor, like how it happens in copper when we switch on the button to start a gadget. What happens is there is flow of electrons that passes through the wires and eventually it goes to the gadget. For example, if I want uh, an LED bulb or a fan to get switched on, what happens is I switch on the button, no? And then that's when the electrons flow and starts conducting. So I'll take you through this one column first and then we'll come to electrolytic conductors. So in electronic conductors, conduction do not involve transfer of matter. Matter doesn't get transferred. What gets transferred are the electrons. There is just flow, movement of electrons. No? Third, conduction process do not involve chemical changes. So when it conducts, there is no chemical changes taking place. Okay. The next point, resistance of conductor increases and conductivity decreases with increasing temperature. Okay, so with increasing temperature, what happens is resistance of that conductor increases and conductivity decreases. Now let's come to electrolytic conductors. Okay, here it is about transfer of ions in solutions. Ions get transferred. Okay, so there's transfer of matter also. current flow is accompanied with chemical changes. So yeah, so current flow is accompanied with chemical changes in electrolytic conductors. So when the current flows, so there will be a chemical reaction. So resistance of conductor decreases. Remember, in this case, resistance of conductor increased, no, with increasing temperature, but resistance of the conductor decreases and conductivity increases. So basically, with increasing temperature, the resistance of conductor and conductivity, they behave in an opposite manner. Okay, in electronic conductors and electrolytic conductors. So yeah, so that's the difference between electronic conductors and electrolytic conductors. Quite an important question, a potential question for 2 marks. That's why I've put there 4 points with an example. Let's come to conductivity. What is conductivity? So when we talk about conductivity, we also come across a word called resistance. Especially in physics, in electronics, you must have studied about resistivity and conductivity. No? So first let's take a look at resistance. What is resistance? It is the resistivity, or to have some curve and control over flow of current. Okay. Now resistance of a conductor is directly proportional to the length and inversely proportional to the area of cross section of that conductor. So you can, now this is something that you must be familiar with. No? So this is, it becomes part of the Ohm's law, and in 10th standard you must have studied all this. No, this is just a repetition of it. So resistance is directly proportional to length and inversely proportional to area of cross section of the conductor. So where rho, this constant of proportionality is called as resistivity, whose unit is ohm. Okay. So resistance, the unit of resistance in SI system is ohm. And what is rho? Rho is ohm meter. Okay, that's the unit of resistivity. So these two concepts are different: resistance and resistivity. Resistivity is this rho, this symbol rho, and resistance is capital R. Okay, so basically resistivity is nothing but resistance of a conductor at 1 centimeter length and area of cross sectional if it's equal to 1 centimeter square. So that's what resistivity is. Conductance. Conductance is the property of conductor. No, obviously. So conductor is something that will conduct. No, so that facilitates flow of electricity through it. So basically, what does conductance do? Conductance, it is a property of any conductor that conducts electricity. No? So what is it? It is the reciprocal of resistance. No, it's just like saying what is the opposite of start? Stop. What is the opposite of up? Down. Similarly, the opposite of resistance would be conductance. Resistance is to stop or to control the flow of current. The conductance is actually promoting conduction. No? So that's why its unit is per ohm or mho, MHO, which is, all the letters are like, they have changed their position. Okay, or it's also called as Siemens. So conductance is what? When I say reciprocal means 1 upon resistance, or resistance is equal to 1 upon conductance. Okay, let's now just quickly derive uh, the relationship between resistivity and conductivity. Conductivity is given by letter K. Okay, letter K is conductivity. Rho is resistivity. Now that we know, in that previous slide we saw conductance is denoted by letter G and not letter C. Now why it's not denoted by letter C? Because in chemistry letter C is for concentration. No, so that's why G is for conductance. Okay, so conductance equal to 1 upon resistance. So we have seen this equation: R is equal to rho into L upon A. Therefore, rho is equal to R into A upon L. I have just rearranged it to get this resistivity rho on the left hand side. Similarly, conductance. What is conductance? Conductance is equal to K into A upon L. Okay, therefore K is equal to G into L upon A. Now, from where did I get this? Because of this, resistance is 1 upon conductance. So, automatically, this L upon A can be written as A upon L. So, when we arrange and equate all these equations, we get conductivity is the reciprocal of resistivity. So this equation, this relationship is very, very important. Okay, so this particular slide, it gives you relationship between conductance and resistance and also conductivity and resistivity. Okay, let's go ahead. So we've looked at resistivity, we looked at conductivity. Now let's look at what is molar conductivity. Okay, molar conductivity is a concept which is related to electrolytic solutions. No? Why solutions? Because only solutions can have molar concentration. Conductivity can be for even for solids, no? Like for copper, aluminum, whichever conductor conducts. So conductivity is that word is applicable for those solids. But to specifically identify electrolytic solutions or solutions which conduct electricity, how do we uh, relate conductivity with those solutions? By introducing new term called molar conductivity. Now, what is the relationship between molar conductivity and concentration? Let's take a look at that. Molar conductivity is denoted by this symbol lambda. Okay. Now, lambda is equal to conductivity upon concentration, or molar conductivity is equal to conductivity into volume of the solution. So let me read this out for you. Molar conductivity of an electrolyte is the electrolytic conductivity divided by its molar concentration of the dissolved electrolyte. Okay, so basically this definition is nothing but what is given in this equation. So lambda is equal to K upon C. So molar conductivity of an electrolyte, let's take a look at the factors affecting it. No? So what are the factors? One thing important is concentration. No? So with concentration, with a decrease in concentration, what happens to molar conductivity? It decreases. I repeat, with decrease in concentration of the solution, what happens to molar conductivity? It decreases. What happens to the variation with conductivity? So that is with conductivity. What about molar conductivity? Okay. So in this case, we saw with decrease in concentration, conductivity decreases. Let's take a look at molar conductivity. Molar conductivity, as I mentioned, it is to do with electrolytes or solutions, no? Which conducts electricity. So molar conductivity of a strong electrolyte varies linearly with the square root of concentration. Now, when I say varies linearly, that means this one decreases, but at a very slow pace. No? So where lambda is molar conductivity, lambda 0 is molar conductivity at zero concentration. Okay, root c, that is c is concentration, is a constant. Okay, so it varies linearly with the square root of concentration. So that's increase or decrease is at a very, very low scale. Okay, so that's about the factors. So basically it's only one single factor, that is concentration, that would affect conductivity and molar conductivity. Now this is something that's very, very important concept in electrochemistry, that is Kohl-Rosch's law of independent migration of ions. Kohl-Rosch's law of independent migration of ions. Now, what is it? What does this law state? It states at infinite dilution. When I say at infinite dilution, means if I keep adding water, if I just keep diluting it, okay, what will happen? Each ion present in that solution, that is cation or anion, migrates independently of its co-ion and makes its own contribution to the total molar conductivity of an electrolyte, now, irrespective of the nature of the ion with which it is associated. So basically, what happens to the molar conductivity at zero concentration is it is the sum of the molar conductivities of individual ions. Now, which are the individual ions in a solution? You must be knowing, my dear students, every substance, every solution, they have their cations and anions. So even solutions would have cations and anions. So the sum of the molar conductivities of cations and anions at infinite dilution. Okay, so if I have to know the molar conductivity of any solution, all I need to know is molar conductivities of individual ions. Which are those individual ions? Individual cation and individual anion. Okay, so this is an important statement on Kohlrausch's law, a potential 1 mark question for the statement only. No, if at all a question comes, write the statement of Kohlrausch's law of independent migration of ions. Okay, so this is what you need to write down with this equation. Let's take a look at applications of Kohlrausch's law. So why is it used and where is it applied? Molar conductivity of an electrolyte can be calculated at zero concentration. No? So conductivity and degree of dissociation of weak electrolytes is something that helps in Kohlrausch's law. So let's see how it helps. Now, alpha, this symbol is a symbol of degree of dissociation. Okay. Now, degree of dissociation is nothing but ratio of molar conductivity at a given concentration C upon molar conductivity at zero concentration. So, alpha is equal to lambda upon lambda 0. Now, dissociation constant K of weak electrolyte. Now, this is something that we had done in ionic equilibria and in chemical equilibrium. No? So, what is the dissociation constant K of weak electrolyte? K is equal to alpha square C upon 1 minus alpha. Okay, this is something that we have studied in previous chapter, no, earlier chapters. So, K is equal to alpha square C upon 1 minus alpha. So, all you need to do is this value of alpha is equal to lambda upon lambda 0. You need to substitute in this equation. So wherever there is alpha here, you need to put that value of lambda upon lambda 0. So after applying that or substituting that value, I get a fresh equation. K is equal to lambda square C upon lambda 0 into lambda 0 minus lambda. So that's your fresh equation. So I can use Kohlrausch's law to find out the dissociation constant. Okay, I can use the dissociation constant. Okay, rather I can get the dissociation constant and also degree of dissociation, no, from Kohlrausch's law. Now how do we measure conductivity? No, in physics practicals you must have seen a Wheatstone bridge. No, so a similar kind of a setup is also used to find out conductivity. No? So what we know about conductivity is conductivity of an electrolytic solution is given by K is equal to 1 upon R L upon A. Remember we had that equation K is equal to G into L upon A. So instead of G, can I put 1 upon R? Yes, I can. Why? Because conductance is equal to 1 upon resistance. So instead of G, which stands for conductance, I can put 1 upon R. Okay. So for any cell, L upon A is a constant. Why is it a constant? Suppose if I know the length of a conductor, if I know area of cross section of the conductor, so automatically I would come to know the value of L upon A. So that's why I call it as cell constant, which is denoted by letter B. So henceforth L upon A, which is length upon area of cross section, it will be denoted by letter B, called cell constant. What is its unit? Per meter. From where do I get that per meter? Length is in meters, area is in meter square. So meter upon meter square will be mm gets cancelled. What remains is one single m in the denominator. So when it goes up, it becomes m raised to minus 1. So thus the new equation becomes conductivity K is equal to cell constant upon resistance. So K is equal to B upon R. Okay, so that's how I can measure conductivity. So this is what it was, right? So measurement of conductivity. So if I know cell constant and if I know the resistance, I should be able to find out the conductivity. Now how do I calculate cell constant? That is determination of cell constant. No? So cell constant is what actually? L upon A or letter B. No? So for example, for KCl solution that is used as a reference. Okay, for as a reference at 1 molar, 0.1 molar or 0.01 molar. Cell constant it was is what? B is equal to K into R. Now this is something that we saw here. K is equal to B upon R, so B is equal to K into R. So I can write down in that manner also. K is conductivity, R is resistance. Okay, so using Wheatstone bridge principle, so resistance of solution upon, so there is one diagram which I will share it with you later. Okay, so R solution upon RAC is equal to Rx upon RBC. So as you can see in this picture representing the Wheatstone bridge, okay, so one arm of the Wheatstone bridge is uh, with that solution of unknown resistance. So as you can see in this equation is basically derived from the Wheatstone bridge principle. So our solution is something that we need to find out. Rx is unknown resistance. Okay, this Rx is something that's over here. It is the resistance of the known conductor. Okay, RAC, it's the resistance that is obtained when this sliding contact, this F is the jockey, that is the sliding contact which moves from A to C. So once you get the resistance of AC, okay, resistance BC. Now this RAC and RBC you may not get it directly because this RAC is directly proportional to the length. So I can replace this RAC with length AC, RBC with length of that conductor BC. No? So once I know length of AC and length of BC, I need to just replace it with RAC and RBC. So R solution upon LAC is equal to RX upon LBC. Since we already know the value of RX, R solution is equal to Rx into length of AC upon length of BC. So this is how we can calculate the resistance of unknown solution using Wheatstone bridge principle. Okay, so with this we can also calculate the cell constant with this formula B is equal to K into R, and we can also find out the resistance of solution. Now, why is it mentioned determination of cell constant? Because cell constant does require this value of R. Okay, now this R comes from where? From after calculating all this, we get this value of R. So once I know the value of R, once I know the value of K, will I be able to find out the cell constant? Yes, I can. Okay. What about determination of conductivity of the given solution? So can I be able to find out the value of K? Yes, I can. So once I know the cell constant B, there is a formula. K is equal to B upon R. No, I will be able to find out the conductivity also. Will I be able to find out the molar conductivity? Definitely yes. Because if I know the value of K and if I know the concentration of that solution, then I should be able to find out molar conductivity also. Okay. So that was about conductivity and molar conductivity. Let's move on to another concept, okay, about cells, different types of cells. No? So let's begin with that. In this chapter, we'll be studying about electrochemical cells. No, electrochemical cells are the cells which convert electrical energy into chemical energy and chemical energy into electrical energy. Before that, let's take a quick look at the different terminologies. So what is metallic conduction? In metallic conduction, charge transfer occurs through metals by the flow of electrons. For example, copper, aluminium, all these things that you see around which conducts electricity in the form of solid, no, they are metallic conductors and it undergoes metallic conduction. What about electrolytic or ionic conduction? This is something that's easy to guess. This kind of conduction you'll find it in aqueous solutions, basically electrolytes, no molten electrolytes or liquid electrolytes. You'll find electric current flowing. So such kind of conduction is called as electrolytic or ionic conduction. Let's go ahead. So electrochemical reactions. What are electrochemical reactions? Very simple reactions that occur in electrochemical cells. No, as I mentioned, what are electrochemical cells? They are cells in which the energy exchange takes place from chemical energy into electrical energy and from electrical energy to chemical energy. So we require electrodes in electrochemical cell. We require electrodes. What are electrodes? Electrodes are surfaces on which oxidation or reduction half reactions occur. Remember, my dear students, I started this chapter by talking about redox reaction. What is the main principle of electrochemistry? Redox reactions. Redox reactions must occur for electrochemical reactions to take place. So if I want redox reactions to take place, Don't you think I need oxidation and also reduction to take place? Definitely yes. So where does that happen? It happens on the electrodes. What are the two types of electrodes? Cathode and anode. Okay, so at cathode there are electrodes at which a reduction occurs. So how you'll remember? Cr, cathode reduction. Automatically the other one becomes anode, oxidation. So electrodes at which oxidation occurs. So reduction would be cathode, oxidation at anode. So these are the two different electrodes that are there in the electrochemical cell, okay, in the form of cathode and anode. As I mentioned, in cathode, reduction takes place, and in anode, oxidation occurs. So that's how simultaneously you will see redox reaction taking place. So what are the types of electrochemical cells? There are two types of electrochemical cells. One is electrolytic cell, and the other one is voltaic or galvanic cell. When I was talking about electrochemical cells, that time I did mention what happens in these cells is conversion of electrical energy into chemical energy or chemical energy into electrical energy. Now, these two cells will precisely tell us what exactly happens in which cells. Now, electrolytic cells, what happens over here is electrical energy gets converted to chemical energy, which means to this cell there is an electrical source which is provided. That source ensures a chemical reaction takes place, resulting into formation of chemical energy. Okay, so this is actually a non-spontaneous reaction. Non-spontaneous, why? Because electrical energy is required. A source of electric current is required to force a reaction to occur. Okay, so such kind of equipment is called as an electrolytic cell, which converts electrical energy into chemical energy. What about voltaic or galvanic cells? It does the other way around. It converts chemical energy into electrical energy. So here it's a spontaneous uh, process. In this, a chemical reaction which is existing, it produces electricity. No? So for example, dry cell, lead storage cell. So all these are voltaic or galvanic cells. Okay, so especially your ever ready batteries, so all those cells, they are use and throw cells, isn't it? So what happens exactly over there is it produces electricity. No, so for example, if I'm using my mobile phone, no, so the mobile phone, when I carry it, that time I'm not plugged to the phone is not plugged to the electrical source. No, so that means there is already a chemical reaction that is allowing that electrical energy to function the mobile phone. So mobile phone basically functions because of the reaction that is allowing it to produce electrical energy. Okay, now let's take a look at both the cells one by one. What are electrolytic cells? So just now I mentioned electrolytic cells converts electrical energy into chemical energy. To avoid any confusion, my dear students, this electrolytic cells, the spelling starts with letter E. So when you are talking about electrolytic cells, you will say conversion of electrical energy into chemical energy. So electrical energy comes first and then chemical energy. Okay. So automatically the other one, that is voltaic cell or galvanic cell, would mean it converts chemical energy into electrical energy. First one, first electrolytic cell, that is electrolysis of molten NaCl. There is a difference between liquid NaCl and molten NaCl. Molten is when a solid is fused. A solid is fused. Liquid NaCl means when there is water involved in NaCl or a solution is made using water. Molten is when a solid is fused. Okay, so for any electrolytic electrochemical reaction, what should take place? Reduction and oxidation. Why is it called half reaction? Because the overall reaction is the combination of reduction and oxidation. Remember what reaction we want? We want redox reaction. We don't want individual oxidation reduction. Individual oxidation is a half reaction. Individual reduction is another half reaction. So when both the halves they come together, I get a net cell reaction, which is my redox reaction. Okay, so what happens in molten NaCl electrolysis is Na plus and E minus. Okay, so since this is cathode reaction, that means reduction takes place. That means gain of electrons. Reduction means gain of electrons. Now what is oxidation? Oxidation means loss of electrons at anode. No, so when both the left hand sides I add and when both the right hand sides I add, I get this net cell reaction.